Hi everyone, my name is Javier Morlana and I'm going to present you my work, Topological SLAM in colonoscopies leveraging deep features on topological priors, a work developed with the help of my colleagues from University of Zaragoza. Our work is about building topological maps for the colon. The best prototype of a topological map is this underground map, where we have nodes and edges. The nodes represent the stations of the underground, and the edges represent traversability link between them, meaning that we can travel from one station to the other if there is a link between them. The state-of-the-art software for building maps for the colon is SLAM, that is a metric 3D SLAM, able to build a small 3D maps for the whole colon, but due to the limitations and the challenges of the colonoscopy procedure, like this constant occlusion, these liquids, these deformations, if we use this software out of the box for building a topological map, what we will get is this linear graph where we build all these small submaps and put one after the other. Unfortunately, this not represents fully the complexity of the procedure, and it is not able to build a single node for a colon location, but split a lot of maps for the same colon location as it is not able to merge them. What we want to have in colon SLAM is a graph more like this, where all the traversability links represents the complexity of the procedure, and each node is a color location that group a lot of submaps that are co-visible between them. Going a bit more in detail, I'm going to explain what are the differences between metric and topological maps. Metric maps are composed by 3D camera poses that represents the trajectory of the endoscope, and 3D points that represents the cavities traversed during the exploration. On the other hand, topological maps are composed by nodes that represents different colon locations, field of images depicting this colon location, and also edges that represent the traversability between different nodes, meaning that we can travel from one colon location to the other. As we observed before, when we try to build maps from colonoscopies with a 3D state-of-the-art SLAM, what we get is several submaps from the same location, where each submap has a 3D point cloud representing the extractor and the keyframes that were used to build this map. This map splitting is caused by several reasons, the first one being the constant traffic losses that occur in colonoscopies, provoking the SLAM to have to build new maps all the time. Once we have several submaps, a traditional algorithm should be able to recognize that two places are the same just by visual similarity, but this kind of algorithm fails in this task. Another reason is that the environment is deformable, so we are not able to find a 3D alignment that can align the two maps. This causes that we have good short-term co-visibility between inside the submap, but we are unable to detect revisited places, and we are also unable to build global and meaningful maps. Our work tried to find these global and meaningful maps by focusing on the visual recognition task, finding co-visibility relationship between different keyframes of submaps. For this purpose, we present colon SLAM. Colon SLAM leverage on the good short-term co-visibility that CUDA-CIF SLAM is able to find between these small submaps, and use several algorithms to find good co-visibility relationship between these submaps, building a rich topological map. Our topological SLAM algorithm is nicely simple. So let's say that we have already built this graph, and the camera is located in the last node in the graph. Topological SLAM will build a new submap, and we have to answer a simple question. Is this place already in the map or not? If yes, we will update a node already built in the graph. If no, we will create a new node, because this place is new. In this case, the place is not already in the map, so we will have to create a new node. We will create a new node by adding a node to the map and a new traversability edge, and we will move the camera position to the last localized node. Then we keep processing the video and get a new submap from CUDA-CIF SLAM, answering the same question as before. In the case that this place has already been mapped, what we will do is update a node with the new submaps and maintain the camera position in the previous spot. In the end, our graph is composed by nodes and edges. The edges represent traversability links between different color locations, and the nodes represents a color location, and stores inside all the submaps from CUDA-CIF SLAM that our algorithm recognizes as co-visible between them. So now that we have explained the column SLAM algorithm, we can observe it working on a real sequence, building a new topological map from the scratch. In the entry phase, a lot of new nodes will be created as the endoscope is just making his way through the end of the column. But we can observe that column SLAM is able to locate to relate a lot of covisible submaps that CUDA SLAM were not able to relate in the first place. And we can see that it's quite precise. In the video, the green bullets represents correctly merged submaps, while the red ones represent wrongly merged submaps, observing that our system is quite precise in the visual recognition task. Now that we have explained the algorithm, there is a big question still remaining. That is, how do we find this covisible relationship between different submaps? We have two ways in this work. The first one is by global features with our L network. Our L network is composed by a backbone that is initialized with EndoFM, the foundational model for endoscopies. This backbone extracts a global descriptor for each image. So for a pair of images, we subtract these two descriptors, obtaining a global descriptor G that is forwarded through MMLP and obtaining a score that helps us to decide if these two images come from the same place or not. This network is trained with the cross-entropy loss in the endomapper datasets, and we use it to find covisibility between submaps. For this, we compare exhaustively each keyframe in one submap to the other, and finally we get an aggregated score that helps us to decide if these two submaps are from the same place or not. On the other hand, we have local features with LightGlue. LightGlue is a powerful image matching algorithm that is able to relate pixel to pixel from two images depicting the same scene. So ideally, for two images of the same color location, we will obtain a lot of matches with a coherent transformation, meaning that the system is able to predict that these two images come from the same place, like it happens in these cases, where the algorithm matches a lot of points and we can predict that these are from the same place. But unfortunately, for some images that suffer a lot of viewpoint changes or deformation, the system is not able to match a lot of points while they are from the same place. And unfortunately, the network also gives some false positive, meaning that two images from different places are predicted at being from the same color location, while they are not. In colonoscopy, we have observed that it's quite important to include some priors. So the colon is a quite linear environment, meaning that you can jump from the sequence to the rectum in a single edge. So we model this through our topological priors that, given current position, we constrain the search of covisibility among the nodes at some distance in the graph. For example, in this case, for the position 18 and a window of size 5, the search window is constrained to this, helping us to boost the precision of our place recognition and to build better maps in the end. Yeah, now that we have explained all the pieces from column SLAM, we can finish the previous sequence and observe the withdrawal stage. We can observe that our algorithm is able to model well these back and forth movements that happens in colonoscopy when the doctor comes back and comes for observing a place of interest, and our algorithm is able to find a lot of covisible relationship between different submaps that were not merged by the SLAM in the beginning, thanks to our visual place recognition algorithms and our submap to submap comparisons. We choose to evaluate the endomapper dataset, specifically in sequence 27 and sequence 35. We built a ground truth topological map thanks to the annotations available in the dataset made by the doctors. So in this ground truth topological graph, all the submaps belonging to the same color location are merged, and we evaluate the precision and recall of different algorithms in finding this covisible relationship. We compare against two state-of-the-art networks in colonoscopy visual place recognition and against LightGlue. Comparing against the network, we observe that our proposed network is the one that has the best precision and recall balance. Interestingly, the topological prior improves the results in all cases. It's notable that our network with topological prior gets similar precision to LightGlue with very high recall and lower runtime. And the full approach, combining the covisible relationship found by LightGlue and our network with the topological prior, gets a very high precision of 90% with a very high recall of 70%. Here we can see some qualitative results for the two sequences, where each row represents a node built in the topological map, and each column represents a submap merged in this node, where we can see one image per each submap. We can observe that our algorithm is able to find co-visible relationship against very huge conditions, like we can see some viewpoint changes, some illumination changes, some fluids covering the camera, and even some surgical operations. So to sum up, we started with this sequence of submaps built by Topological SLAM that represents the procedure in a very simplistic way. And after applying our column SLAM algorithm, we're able to build this nice topological graph that quite represents the complexity of the procedure with this rich graph with a lot of traversability edges that represents the back and forth movements of the endoscope during the procedure, and each node representing a color location with a lot of co-visible submaps in it. For conclusions, we have presented column SLAM, the first topological SLAM able to map the whole column, and we have observed empirically that influxing priors and this map-to-map visual recognition has proven crucial in building good maps and finding good co-visible relationships. As future work, we can see that specialized image matching for endoscopy is still to be fully explored, and we have to build long-term relationships like entry and withdrawal and second visits that are a limitation of this work that will unlock personalized patient maps that will be applied in real use cases like navigation assistance and disease monitoring. I would like to say that our endomapper research project is transitioning into a more commercial or entrepreneurial stage in the Cartoscope project. So if you want to know more or study potential collaboration, please ping me out. And thanks for listening. This is Topological SLAM in colonoscopies leveraging these features and topological priors. And the code will be available in the GitHub, and this is my social media if you want to follow.